In this section, we're going to look at growth models for biological populations. We can think of a population as growing in the same way that money in a savings account with compound interest grows. So you start out with a beginning population, which will be the principal in your savings account. Assume that it grows at a constant rate, like the interest rate, for each year or compounding period. So generally we'll have a year here, but this could be another period like hours, days, weeks, etc. And this is a simple model which is best for short periods of time. So let's go ahead and look at the formula. This is exactly the same as the formula for a savings account with compound interest. So if we have an initial population P, an annual growth rate R, then the total population after n years is going to be given by P times 1 plus R to the n. So let's go ahead and look at an example. So we're going to look at the U.S. population. And the U.S. population has increased at an average effective growth rate of 0.95% per year to 310.5 million people at the beginning of 2011. So rounding to the nearest million, what is the anticipated population at the beginning of 2015? So we're going to go ahead and use our geometric growth formula. P is the initial population, so the population at the beginning of 2011 was 310.5 million. That's a pretty big number. R is the growth rate, is 0.95%. And if I convert that to a decimal, that's going to be equal to 0.0095. N is the length of time we're looking at, and here we're looking at a growth rate per year, so we want to know how many years later, and we're looking at 2015, so that's 4 years. So if I plug that in, then the anticipated population at the beginning of 2015 is 310.5 million times 1 plus R is 0.0095 to the power of n, which is 4. Now I'm going to round this to the nearest million, and that's going to give me 322 million people at the beginning of 2015, if we keep that growth rate of 0.95% per year. Now let's look at what happens if the effective rate of growth changes, if it goes up to 1.2% per year, or if it goes down to 0.7% per year. So we're going to use the same formula. A is equal to P times 1 plus R to the power n. And again, we're going to look at the years from 2011 to 2015. And our initial population was 310.5 million. So what happens if my rate of growth is 1.2%? Well, in decimal form, that is 0.012. And the amount of time we're looking at is still the same. We're still looking at 4 years later. Then the anticipated population, if I've got a higher growth rate, for the beginning of 2015 is 310.5 million times 1 plus 0.012 to the power 4. And if I round that to the nearest million, I'm going to get 326 million people. Now what about if my growth rate is 0.7%? So what if my growth rate is lower? I'm still starting out with my same initial population. The decimal form of 0.07% is 0.007. And I'm still looking at the same time period of 4 years, so n is equal to 4. Then my anticipated population is going to be 310.5 million times 1 plus 0.07 to the power of 4. And that's going to give me a population of 319 million if I round to the nearest million. So that's a difference of 7 million people over 4 years, with just a difference of 0.5% in the growth rate. So geometric growth is a very simple model for growth. In fact, if a population keeps growing by a fixed percentage each year, then like a bank account accumulating interest, it would eventually grow to astronomical numbers. So no population can keep growing forever without a limit. The size of a population is constrained by things like availability of resources such as food, energy, and space. So we might need to take this into account for more complex and long-term models of growth. So let's talk about carrying capacity. The maximum population size that an environment can support with the available resources is called the carrying capacity, and that's denoted by M, and the M stands for maximum. So as a population increases towards the carrying capacity, the growth rate tends to decrease. And if the population ever exceeds or goes past the carrying capacity, then there aren't enough resources to support that population, and the growth rate is going to become negative and the population is going to decrease. One way to take this into account is with the logistic model for population, and it gives us this formula for the amount of growth P prime based on the effective growth rate and the current population and carrying capacity. So let's take a look at an example of using this formula. And we're going to use this formula instead to predict the U.S. population. So let's suppose that the U.S. has a carrying capacity of 400 million. Then the U.S. population increased at an average effective growth rate of 0.95% per year to 310.5 million at the beginning of 2011. So this is the same setup as our previous example, but now we've got a carrying capacity of 400 million. And we're going to use the logistic model to find out what the adjusted amount of growth of the population is through the beginning of 2012. So we're just going to look at 1 year here. So here, P is my initial population, so P is still equal to 310.5 million. R is the effective growth rate, so that is still 0.95% or 0.0095 in decimal form. M is the carrying capacity now, and that is 400 million. So I can plug that into my formula to find P prime, the amount of growth. That's going to be 0.0095 times P is 310.5 million times 1 minus P divided by M, so 310.5 million divided by 400 million. And that's going to give me a growth of 660,000 people in the year from the beginning of 2011 to 2012. So according to this model, if we keep doing this, at the beginning of 2015, the U.S. population will be about 313 million, which is lower than any of our predictions from example 1. Finally, let's look at this graph, which shows different models for population growth. So here we can see the U.S. population by census year. The black squares on the graph represent the actual measured population. The red line here represents the geometric or exponential growth model starting around the year 1870. And this light blue line here shows the growth based on the logistic model according to the census through 1920. Now, at this point in time, they thought that the carrying capacity of the United States was about 200 million. So you can see if we draw a dotted line here at around 200 million, that the population increases but levels off as it goes towards 200 million. As we said in the last example, we now think that the U.S. has a carrying capacity of about 400 million. So if we started here on our chart with the last measurement in the year 2000, 400 million is off our chart a little bit up here, but we'd have a dotted line around here. So if we looked at the logistic model starting now, we might expect growth to look kind of like this, so to curve up and then to level off as it approaches 400 million. So that's the end of this section. Things that you should know. You should be able to predict population growth over short spans of time using the geometric growth model, and know that what carrying capacity is and how it affects growth rates.